Given a choice between two knives, which would you prefer? A forged knife or a stamped knife? And why would you care one way or the other? What do you expect a forged knife to do that a stamped knife couldn't do? Well, in this video, we're going to go over that. We're going to try and understand exactly what is metal forging, how it's done, as well as what the benefits are. So stay tuned, and if you haven't seen any of my other manufacturing videos, go ahead and check out my playlist, and I'll be back in a minute to talk about this process called metal forging. Hi, this is Professor Cummings. I wanted to get back with you on this question of which is better, a forged knife or a stamped knife? You know, if you've ever seen the commercials, you notice that they actually charge a lot more, or been to one of these kitchen stores, they charge a lot more for a forged knife and promote forged knives over anything that's been stamped. So why is that? Why would this be a better product? Well, in order to understand that, we have to understand exactly what is metal forging. All metal forging is a type of forming process, metal forming process. It falls under the umbrella of things like cold rolling and hot rolling. So it's actually taking the metal, you're not cutting any material away, and you're just forming it into the shape that you want. It's actually the oldest recorded metalworking process. It's older than machining, older than grinding or any of the other processes that you have. So it dates back 4000 BC. And you can see this in things like blacksmiths, short horseshoes, swords, shields, helmets, armor. All these things were forged back centuries or millennia ago. All it does is uses compressive forces to actually shape the metal. That's why you see in movies or in the image above where there's a hammer or some sort of a die on top and a lower die beating the metal into shape. So that's all it does, is using compressive forces to actually shape the metal. So what actually is going on with metal? So to understand metal itself, you actually have to understand metal is actually a structure made up of a series of grains. So all these grains come together and they form a metal shape. So this picture you see before you is bismuth. Bismuth, if you take it to a molten state, actually heat it up till it's a liquid form. It becomes liquid at about 600 degrees or so Fahrenheit, and you allow it to cool down, you'll end up with these really pretty structures of grains, crystals, or grains that come out in this rainbow form. Now, what it does is it goes through an evolution from this metal all the way to its solid. And all metals do this. Now, that's what bismuth looks like. Over here on the right, you have steel. So if you heat steel up to the molten state and allow it to cool down, you'll actually start to form these crystals. So the crystals will form in the molten steel and they will gradually grow into these tree-like structures until finally the entire piece of steel has solidified. Now, if these little crystals look familiar to you, they should, because they look a lot like this. This is snow crystals up at the upper top, or upper right. And these snow crystals, snow actually forms in the same manner. They start these tree-like structures that gradually grow until finally you form a full structure. And these little crystals, these tree-like structures, are what's known as dendrites. So dendrites are just the crystals that start in metal from the molten state. We'll just say the liquid state, whether it's snow or whether it's steel. So it's from that liquid state, and they actually start at the start of the solidification process into these tree-like structures. And gradually that becomes what we see as solid steel. So let's look at more of that process. So we start off with dendrites in the steel, and as it goes, it starts to grow until you get something that's solidified, and these are grains. So these are steel grains that have grown from dendrites and then solidified until what we see here is steels, and you see this at 30 microns right here. So 30 microns, so that's steel. So these, even though this is blown up a lot, you can see that these are relatively large. They're irregularly shaped. They don't have a really consistent size, and there's a whole lot of issues with the boundaries that kind of show up and aren't necessarily consistent. So what you have is you have very coarse grains, very large coarse grains there's a lot of internal porosity. So that's what these are. These are internal porosity within the steel itself. And these porosities and these large irregular shaped grains have consequences. Larger grains mean lower strength, it's more brittle, as well as it's much more prone to fatigue failure, and due to the porosity. So if you have a design and you use steel that was made just straight from a casting, even though it's not guaranteed, it's much more prone to a fatigue failure, meaning if you load it and unload it, different types of cyclings, different types of cyclic loading, you're much more likely to have a fatigue failure due to these issues that you have because of the grains that the metal is made up with. So the very structure of the metal, the grains that they're made up of actually form the different types of mechanical properties that you're going to get in the final metal. So what can you do to manipulate these grains so that you get much better mechanical properties? Well, that's when forging comes into play. What we have here is a phase diagram. Okay, so here at the top is the liquid state. So all this area here is in the liquid state. Down here at the bottom, you have things in the solid state. So this is all solid. Over here on the right, this is the temperature. Or excuse me, on the left is the temperature. So this is in Fahrenheit, and over here is Celsius. So that's the temperature, and down here is the composition of the two metals that are making up the alloy. That's not really as important as I want you to see what the rest is. So here in the middle between this liquid state and this solid state is what's known as the mushy zone. This line is known as the liquidus. It means we've crossed into full liquid. And this line here is the solidus, which means we've crossed into solid. And over here on the right, you've got, these are the depicting the crystals. So as it crosses this liquidus, you're getting the start of the dendrites. And you go into the mushy zone, the dendrites grow, and then as you leave into across the solidus, the dendrites have fully formed into crystals. So what's forging doing? Forging is actually heating metal up to the point where it has gone into that recrystallization stage. So you've heated up actually into the recrystallization stage to where the dendrites are actually starting to form, and before the crystals have fully formed. So the metal has not fully set yet, if you want to think of it that way. It hasn't fully set yet, and you now have an opportunity to start manipulating the way the actual grains are going to form when it becomes a fully solid metal. Now the way that's done is if you take a type of metal and heat it up to where it's actually above that crystallization stage, and you have an upper die right here, an upper die, and a lower die. So this is also a die. So we just say lower die. So an upper die and a lower die that are coming together in that beating process, that compressive process. What you can see here is that you're actually beating the metal down. You're actually changing the shape, and you're therefore changing the size of the crystals as it comes out of this, out of that die process. And it can be a single die, it could be a series of dies, but you're actually changing the size and shape of the crystals, which in turn will actually give you much smaller grains. You're also going to get rid of a lot of the porosity inside of that metal as you actually go through the forging process. So you get smaller grain sizes, less porosity, but something else happens in this. You actually start to align your grains. You get an aligned grain flow. So this is a really important part of the process actually becoming a stronger metal. You're actually changing the structure and the mechanical property of the metal at this point because of that new grain flow that you're giving it. And all this together makes for a much more stronger, much more ductile, much less likely to fatigue piece of steel or whatever metal you're forging than if you had just left it in the cast state. So what are the benefits of, say, a forged knife versus a stamped knife, or in this case, say just machined? So it's machined and stamped have a lot in common. So a forged knife and a stamped knife. And while we're at it, let's look at a cast product as well. So here we have three different products made the exact same way through the exact same dimensions. just three different types of processes, or same material, same dimensions, three different types of processes. If we look at the cast process, you can see that the grains are random and there's no real alignment to them. There's no real order to them. So you can say they're unrefined grains. And this is a much more brittle material. There's not the same alignment. There's much more likely going to be porosity. So there will be much more likely chance of fatigue failure. Here at machining, which is got a lot similar to stamping in that you're actually removing material. And stamping is a little more abrupt, but you're still removing material, and you're breaking a lot of the grains. You're breaking a lot of the grain boundaries in order to form the shape that you want to form. So again, a lot more likely to have fatigue failure with a machined process. Not nearly as ductile as forge. Here in the forging, you've got much better consistent grain flow. None of it's been broken. They've all been formed and aligned to the shape that you want. So this is going to be a much stronger material, much more ductile material, and a lot less likely to have machine failure or fatigue failure. All right, thanks a lot. This is Professor Cummings. So if that video was helpful to you at all, go ahead and subscribe to my channel. I do videos on manufacturing as well as different engineering topics. Please share the video to anyone you think might be able to benefit from it. So you can subscribe to me on YouTube. You can also follow me on Twitter, where I go through a lot of different engineering and manufacturing topics up to date, talking about the skills gap and Industry 4.0, or the fourth industrial revolution. You can also follow me on Google+. I have two fairly active communities. One is manufacturing skills and education, where I talk about obviously manufacturing and manufacturing skills, manufacturing technology, and I try to help people showcase their companies on that channel. And then there's the Engineer's Reference, where I talk about general engineering activity, a lot on automation, a lot on just like new technologies and different types of math applications and different things that engineering goes through. So another pretty active community. And anytime you see my little logo, the infinity, double infinity, you can know that I've got my presence there. Again, thanks for watching, and I'll see you on the next video.